So far in this chapter, we've looked at all of the formulas for calculating energy, and then we looked at the energy bar graphs to visually represent energy and energy transfers. So in this section, we're going to put the two of them together through a series of examples. So the way all of these problems work is we're basically using the law of conservation of energy, that work energy theorem, where we have all the initial forms of energy and all the final forms of energy, and that was on the last slideshow. And then we're going to make an equation based on the relevant energies in the problem, substitute in the equations and the numbers, and then solve for whatever the question is asking for. So that's our basic strategy. Here's how we do this in a practical example. So, okay, it's only somewhat practical. Willie Make It, that's kind of a silly name. So we have a guy standing on a cliff, and he's 5 meters above a trampoline. I tried to find a picture of a guy standing on a cliff over a trampoline. This is the closest I could come up with. It's a blob. If you've never seen a blob, they're really fun. Somebody sits on the outside of the blob here, and then the other person jumps down, and then it pops the other guy off. And anyway, that's the closest I could come to. So we have a guy standing on a cliff over a trampoline. So we're going to solve for a couple different things on this. First, we're going to look for his speed the instant before he hits the trampoline. So to begin with, we're going to look at an energy bar diagram just to be able to qualitatively describe which energy transfers are going on. So if he's standing on a cliff 5 meters above the trampoline, we're going to say that the bottom of the problem is 0 meters, or the right at the trampoline would be 0. So that means he has some gravitational potential energy to start with. In this problem, we're not going to be using the energy flow diagram because we're not taking energy into or out of the system. So all the energy stays in the system. We don't need the middle part. So finally, at this point, the way that they ended this problem, he's right above the trampoline. That means all of his gravitational energy has been transferred into kinetic. So those bars are supposed to be the same height, showing that you have the same amount of energy to begin with that you end with. Okay, so now we look at our entire conservation of energy equation. And when we look at this, we don't use all of this. We're only going to look at the parts that are relevant for this problem. In this problem, we start with gravitational energy and we end with kinetic energy. So those are the two that are relevant to this problem. So I'm going to set those two then equal to each other. Depending on the problem, you could have all of those things in the equation. You could have kinetic energy on both sides if it's a different velocity. As long as there's a change in that type of energy, then it is relevant to the problem. In this case, we made it really straightforward, and all the gravitational is going to kinetic. So now we substitute in the formula for each one. Notice whenever you have gravitational and kinetic equal to each other, you can cancel out the mass since it's on both sides. So that makes that a nice equation. If you leave it in, it's fine. It doesn't matter. You'll get the same answer. But you can simplify it a little bit, do a little less calculations, and cancel out the mass. So now we put all the numbers in, and we solve for velocity, always making sure that you do take the square root of your answer to find that velocity. So there's my part A example. Moving on from there, the next one, so now we're going to let him hit the trampoline. How far does the trampoline stretch? So we're looking back at our work energy theorem, and we have, to begin with, well, let's see, where did I begin this one? Okay, so I started at the top of the cliff. You could use that same total amount of kinetic energy he has right before he hits the trampoline, since those two are equal. So you could start with either the total kinetic or the total gravitational, because in this case it's the same total amount of energy. And all of that energy is going to go into stretching the spring. So we have our EG equal to our EL. In this case, we don't have mass on both sides, so it's not going to cancel. And we'll go ahead and put the numbers in there. And the 2,000 newtons per meter should have been given in this problem. I think it was in the original setup. Okay, so you go back and you solve for x, and you get 1.6 meters. Part C. So now in this one, we're going to change our situation a little bit. In real life, you know that you're going to lose a little bit of energy in that situation because you're going to, as you hit the trampoline, you're going to have, heat and that sort of thing, sound, everything, other ways that energy could leave that system. So we're going to account for that and say that we're going to lose 25% of that energy. So here's how we deal with this. So you've got your elastic energy, and we're asking how high he bounces, so I know he's going to go up. So he's going to go up to some height, and that's going to give him gravitational potential energy. So what we're going to say then is if he loses 25% of the energy, we're going to say that he retains 75%. So we're going to say 75% of that elastic potential energy is going to go into the gravitational. So you're going to take that same number, same values, only we're going to put a 0.75 in front of the elastic side. So I put all the numbers in there, and I go through and I solve for height, and I get 3.6 meters, which should be less than his initial height. So that shows that some of the energy is leaving the system, which should make sense if you see something, even if you take a basketball and you just drop it and you let it bounce, it's going to bounce lower and lower each time because it's giving up some of its energy to other things. So same thing here. It should make sense that it would be a smaller height if we've lost some of the energy. Okay, so that's all for that one. The next one we're going to talk about how we use work in these same kind of problems. So here we have Rudolph pulling the sleigh. Normally I get to this chapter after Thanksgiving. This particular year we're actually getting to it a few days beforehand. So there's fewer days between Thanksgiving and Christmas this year for school days. So anyway, sorry for the early Christmas showing. Don't you hate that? So this one, we've got Rudolph pulling the sleigh at a constant speed, and they give you the distance, and they give you a mu k whenever they give you the coefficient of friction that tells you that there is going to be friction in this problem. So to begin with, we're going to start with our energy bar graph. So if the problem starts and he's already moving, he has kinetic energy. However, he does have friction, so you're going to be losing some energy at the end, which means if he's going to maintain a constant velocity, Rudolph has to be doing work on the sleigh and adding energy into it. So I've got my same kinetic energy at the end because I have the same velocity. Okay, so to keep that same velocity, knowing that I'm going to have friction, there's my addition of work. And then at the end, I made my work balance my amount of friction that I'm having. So as the time goes on, Rudolph is putting in more work and more energy is going into friction. But the energy at the kinetic energy at the beginning and the end have to be the same because you're going the same speed. Okay, so we're going to look for a force diagram and then answer a couple other questions that it has with us. So our force diagram, this should be pretty easy by now. We've got normal force and gravity. They don't say he's on a ramp or, it'd be more interesting if he were on a roof or something. But he's on level ground, so normal force and gravity are the same. He has the pull force from Rudolph and the friction force that he is overcoming to keep moving. Okay, so those two are the same since it's moving at a constant speed. And I went ahead and put the numbers in for each of those. Now that I know the normal force, I can calculate the force of friction. So to do that, and I don't think I put the calculation on there, that would be normal force, the 1715, times the coefficient of kinetic friction. Now, I left my friction force positive since I just left to the right positive and to the left negative. However, on my picture, he is actually moving to the left. Now, those are going to be the same values, just opposite signs. If you had flipped them and left friction negative and the pull positive, that would be fine, as long as the pull force and the kinetic friction are opposite signs here. Same size because it's moving at a constant velocity. So next up, we're going to see how much work he does to pull the sleigh 225 meters. So we said work was adding energy into the system. So it depends on how far he pulls the sleigh to know how much energy that requires. So this is where we use the work equation. You know it's the work equation because they gave you a distance, and we know a force since they had us do a force diagram. So I put in the force of him pulling, and then I put in the distance to see how much work that I have. It's a pretty big number, but that's fine. A lot of times the joule numbers end up to be fairly large. That's why you might hear a lot of times they describe these things, large energy things in kilojoules or megajoules or something like this. But we're just going to leave that as 116,000 regular joules. So that's how much work it is, force times distance. If he had been pulled at an angle, then you would have to take the cosine theta of that to find the x component of that pull, because work has to be in the direction that the motion is occurring. Okay, so how much energy is dissipated by friction at the end? So that's a little tricky. You know how much energy he put in as work. You know his speed didn't change, so how much energy has to be consumed by friction? Has to be the same amount. So however much energy he put in as work is what's going to friction. If the work were more than that, then his kinetic energy would be increasing. So that's all that one is, just a concept question. Let's see. Yep, that's what I said. Okay. The next one's going to be power. We're going to save that for the next section. So that is it as far as doing the calculations. Some of these are pretty simple as far as just putting the numbers in the equation. Some of them are a little more complicated when you have to do friction and that sort of thing with it, but we'll practice those in class.